Hi everyone, welcome to lecture number 8 of probability under a GATE complete course, a GATE data science complete course. So in the last lecture we discussed total probability, what total probability is. So probability of an event A, which is not very straightforward to calculate. We have a sample space which is partitioned into n events B1, B2 up to Bn, and probability of A given B1 given B2 is easier to calculate, and also probability of B1, B2, B3 is given. Then what is probability of A? It is just the sum of probability of A given Bi times probability of Bi for all I from 1 to n, right? So we'll use the same law. This is the law, and solve a few more questions. It is very important coming to GATE exam. A lot of questions have been asked from total probability. So let's solve a few more questions. So in a bag, there are 3 balls. So it is a slightly trickier question. Now we have already solved easier problems in the last lecture. In this lecture, we will solve a few advanced problems and GATE previous year questions. So just try to solve this question. In a bag, there are 3 balls. One of the ball is not known to be red. The probability of any of the other ball being red is 0.5. What is the probability that the randomly chosen ball from the bag will be red? Okay, so it's not very straightforward. So what it is given? So there are 3 balls in a bag. So this is our bag. There are 3 balls. First ball is given to be red. It is sure to be red. So probability of this ball being red is 1. Then the other ball can be red or non-red. It can be red or any other color. But the probability of this ball being red is given to 0.5. And similarly for the third ball also, it can be red or not red. Probability of this ball being red is also 0.5. Okay. Now we choose a ball at random from this bag. So what is the probability that the chosen ball is red? So it can be this ball. If this ball is chosen, then the probability of this being red is 1. It is it will surely be red. But it is not necessarily that we are choosing this ball only, right? The probability of this ball being chosen is only 1/3. With the other 2/3 probability, this or this ball can also be chosen. But if this or this ball is chosen, the probability of the ball being red is only 0.5. Okay, so it's very simple. Okay, total probability. So probability of the second ball being red is, so if you choose this ball, the probability of choosing this ball is 1/3. Now if you choose this ball, the probability of the ball being red is 1. If you choose the second ball, probability of choosing the second ball is 1/3. If you choose the second ball, probability of it being red is 0.5. So I'm not drawing the diagram, I'm directly applying the equation, okay? And probability of choosing the third ball is 1/3. And probability of getting a red ball given the third ball is chosen is 0.5. So it is 1/3 plus 1/3 times 1/2. So it's 2/3 times 1/2. So it's 2/3. Okay, so there are 2/3 chances that overall, if you choose a ball randomly from this bag, it will be red in color. Okay, if you want the diagram, I can draw it. So the entire sample space can be divided in 3 parts. You choose the first ball, you choose the second ball, or you choose the third ball. And this is our event, getting a red ball overall. So you can get a red ball given the first ball is chosen, you can get a red ball given the second ball is chosen, or you can get the red ball given the third ball is chosen. Probability of all these 3 is 1/3. Choosing the first, second or third ball. Now probability of red ball given the first ball is chosen is 1. Probability of red ball given the second ball is chosen. It's conditional, not joint. Okay, conditional probability. So probability of getting a red ball given the second ball is chosen, it is 0.5. And similarly for the third ball. Okay, so I just applied the formula and we get 2/3. Cool. So let's see one more example. A bag contains 4 fair and 3 unfair coins. Okay, simple. Again, I always draw. So a bag contains 4 fair coins. They are fair. Okay. What do I mean by a fair coin? The probability of it landing at heads is 1/2 and tails is also 1/2. And there are 3 unfair coins. There are 3 unfair coins. And it is given that probability of getting a heads on unfair coin is 1/3. So probability of getting a heads on unfair coin is 1/3 and tails will be 2/3. Right? Now a coin is drawn from the bag and tossed. A random coin is taken from the bag and tossed. What is the probability that it will land on heads? Okay. So again, like you don't need to draw the diagram every time. So you either can get a fair coin or an unfair coin. So the probability of getting a fair coin so basically you're taking a coin out and then tossing it. So when you're taking a coin out, you can get a fair or unfair coin. You don't know. Okay, you're choosing a coin randomly. So the probability of getting a fair coin is 4 by 7. Right? There are total 7 coins. 4 of them are fair. So probability of getting a fair coin is 4 by 7. So if you're getting a fair coin, given the probability of heads, given that you got a fair coin is what? 1 by 2. So this probability is probability of getting a heads given that you chose a fair coin. Or you can get an unfair coin. Unfair coin, the probability is 3 by 7. Now probability of getting heads given that you got an unfair coin is 1 by 3. It is given to be 1 by 3. So this is the total probability. So this is 2, this is 1. So it's 2 plus 1, 3 by 7. So there are 3 by 7 chances that finally the coin will land on heads, and 4 by 7 that the chances that finally when you toss the coin it will land on tails. Okay, you can draw the diagram again. It's not required. The entire sample space can be divided into fair and unfair, and then you are tossing the coin. Okay. So there is another version of the same problem. So the same configuration is given: 4 fair and 3 unfair coins, and now 2 coins are taken out from the bag and tossed. Okay. So what happens? There are 4 fair and 3 unfair coins, and probability of getting a head from the fair coin is 1 by 2. Probability of getting a head from the unfair coin is 1 by 3. Now 2 coins are taken out from the bag and tossed. So nothing is given. So basically you're taking 2 coins. So they are not uniform. Okay, you're taking the first and second coin together. So both of them can be fair. One can be fair and one can be unfair, and both of them can be unfair coins. Right? So either one of these 3 cases can happen. So now what is the probability that both the coins will land on heads? That's what I need to calculate. So firstly, let's calculate what is the probability of getting 2 fair coins. So now we come to counting. Okay, in counting we have seen basically there are 7 coins, and in how many ways can we get both fair coins? So probability of getting both fair coins is what? So in overall, how many cases do we have? If we have 7 coins in a bag, in how many ways can I take out 2 coins? Okay, 7C2, right? And in how many ways both of them will be fair? 4C2, right? And similarly, we have 7C2 cases. In how many ways will be 1 fair and 1 unfair? So 4C1 into 3C1. Okay, so you take 1 fair and 1 unfair coin. So there are 12 possible cases. Similarly, when you what is the probability of getting both unfair coins? 3C2 over 7C2. Right? So if you want to verify that these numbers are correct, you can just sum the numerators. The sum of the numerators should come out to be the denominator, right? Because only one of these 3 cases should be can happen. Basically, the sum of these 3 probabilities should be 1. So what is 7C2? 7C2 is 7 into 6 over 2, which is 21. What is 4C2? 4 into 3 over 2, which is 6. What is 4C1 into 3C1? It is 4 into 3, which is 12. What is 3C2? 3C2 is 3 into 2 over 2, which is 3. So what is 12 plus 3 plus 6? That is 21. So right, yeah. Sum of the numerators comes out to be 21, which means only one of these 3 cases can happen. And we calculated the probability of each one of the configurations. Now, what is one of these 3 cases can happen. So in total probability terms, this is our sample space. Either you can get both fair, or you can get 1 fair, 1 unfair, or you can get both unfair. Now this is your event. What is the probability of getting both heads? Both of them landing on heads. So so let's call them like 3 events. Let the events be E1, E2 and E3. Now probability of both landing on heads is probability of event E1, which is 4C2 by 7C2, which is 6 by 21, times probability of both heads given both of them are fair. probability of both heads given both of them are fair. So which is 1 by 2 into 1 by 2 plus probability of one fair and one unfair coin, which is 12 by 21 times getting both heads given that one is fair and one is unfair. So on the fair coin, the probability of getting in heads is 1 by 2 and on the unfair coin, the probability of getting in heads is 1 by 3 plus if both of them are unfair, which means the probability is 3 by 21 times if both of them are unfair, the probability of getting both heads is 1 by 3 into 1 by 3. So you just need to solve this entire expression, okay? And you'll get 0.183. So there are 18% chances that both the coins will land on heads. Generally, like in GATE, you won't be asked this much complicated question, but yeah, if required, you can answer it, okay? It involves some concepts of counting and probability both, and it involves total probability as well. So this is how you solve it. Cool. So this is GATE 96 question. Two dice are thrown simultaneously. The probability that at least one of them will have a 6 facing up is what? So you are throwing two dice simultaneously. So this is not necessarily from total probability, okay? It's very simple to calculate. You don't need to apply total probability here. It's just a previous year question. That's why I added it here. The probability that at least one of them will have 6 facing up is, okay? So you can actually enumerate all 36 cases, right? You can enumerate all 36 cases. So from 1, 1 to... Okay, so at least one of them having 6 facing up. So what are the total cases? So let's say the first dice is having a 6 on the top. So the second die can have 1, 2, 3, 4, 5, 6, anything. So this is the first die and this is the second die. Or you can have a second die facing a 6 and in the first die you can have anything from 1 to 6. Right? But here we are overcounting one case. 6, 6 is present here also and 6, 6 is present here also. So there are 6 cases here, right? 6, 1, 6, 2, up to 6, 6. And what are the cases present here? 1, 6, 2, 6, up to 6, 6. So I should not include 6, 6 again, right? I should not overcount it twice. So let me just add up to 5, 6 only. Because I already added 6, 6 here. So what is the total number of cases? 6 plus 5, which is 11. So there are 11 cases in which you get at least one of them having a 6 facing up, right? So the total probability is 11 by 36. Okay, these are the 11 cases in which you get at least one 6. Cool. Now let's see this GATE 2007 question. Suppose there are two coins. The first coin gives heads with probability 5 by 8 when tossed. The second coin gives heads with probability 1 by 4. One of the two coins is picked up at random with equal probability. What is the probability of obtaining heads? Very simple question, right? This is the simplest question which can be asked in total probability. There are two coins. One of them is chosen randomly at tossed. So like choosing this coin, the probability is 1 by 2, and this coin also the probability is 1 by 2. If this coin is tossed, the probability of getting in heads is 5 by 8. And the tails will be 3 by 8. If this coin is tossed, the probability of getting in heads is 1 by 4 and tails it is 3 by 4. Now one of the coins is chosen randomly and tossed, what is the probability of getting heads? So if first coin is chosen, the probability is 1 by 2. And if first coin is chosen, the probability of getting in heads is 5 by 8. Plus, if the second coin is chosen, the probability of getting in heads given the second coin is chosen is 1 by 4. So this is the total probability of getting in heads. Right? You can draw the diagram. And this is the first coin, this is the second coin, this is the probability of getting heads. Probability of getting the first coin is 1 by 2, second coin is 1 by 2. Probability of getting in heads given first coin is chosen is given to be 5 by 8, and probability of getting in heads given the second coin is chosen is 3 by 8, and I have just applied the law of total probability here, right? So what is this value? You can calculate it. So how to do this quickly? Make this also 8 and make a 2 above. So this will be upon 16, so it will be 5 plus 2 upon 16, so it is 7 upon 16. Cool. So this is the probability, total probability of getting in heads. So this is GATE 2019 question. Two numbers are chosen independently and uniformly at random from a set 1 to 13. The probability that their 4-bit binary representations have the same most significant bit is. So this again need not be from total probability. Okay, so I just added this question to tell you that not everything is from total probability. Okay, so you just need to see the question and like understand what it is trying to ask. So two numbers are chosen independently and uniformly. What does uniformly mean? I told you, if uniformly is written, it means that you choose the first coin, the first number, and then put it back. Okay, there is no connection of the two numbers which you are choosing. You are not choosing, so if you are choosing 2 in the first go, you can again choose 2 in the second go. Okay, and trust me, I made this mistake in the exam, so it's like the simpler problem. See, the more difficult problem to solve is you are choosing a 2 and you are choosing another number, right? You are not putting it back. That is more difficult because that will involve combination 13C2, 6C2 and so on, right? But here there is no combination. It is written that the numbers are chosen independently and uniformly. Okay, so don't make this mistake. Now the probability that their 4-bit binary representation of the same most significant bit. Okay, so this comes under digital logic a bit, but yeah, like it's very simple to solve. So if you know binary representation, we know that 1 is what? 1 is 1. We know that 2 is what? 1 0. And 3 is what? 1 1. You know how to calculate binary, right? And we want 4-bit binary representation. So basically, the 4-bit binary representation of 1 is 0 0 0 1. Of 2 is 0 0 1 0. 3 is 0 0 1 1. 4 is 0 1 1 1 0 0. And so on. 8 becomes 1 0 0 0. This is 8. Right? And 9 is 1 0 0 1. So this is 1 2 3 4. This is 9. Similarly, we are having up to 13. So 13 will be what? 8 and 4 12 and 1 13. Okay, this is 13. So these are all the numbers that we have. So basically I should have 8 this side because we are having, it will be better if I have 7 here. 7 is 0 1 1 1. 8 is 1 0 0 0. 9 is 1 0 0 1. And we have up to 13, which is 1 1 0 1. So these are all the numbers that we have. So, and two numbers are chosen independently and uniformly. So you choose one number, put it back, and then choose another number. Okay, that is okay. So basically, these are independent events. These are independent events. So, and what is the probability that both the numbers chosen have the same most significant bit? See, all these numbers have the same most significant bit. So here the most significant bit is 0. Most significant bit is the leftmost bit. And for all these numbers, the most significant bit is 1. Right? So for all these numbers, the most significant bit is 0. For all these numbers, the most significant bit is 1. So there are, so 1 to 7, how many numbers are there? 7. And 8 to 13, how many numbers are there? 6. 8, 9, 10, 11, 12, 13, right? So there are 7 numbers which have 0 as the most significant bit, and you have 6 numbers which have 1 as the most significant bit. So what is the probability that both the numbers chosen have the same most significant bit? It is like somewhat related to total probability. How? So if you choose, so let's say this is set S1 and this is set S2. So basically the probability of getting same most significant bit is what? Same MSB is what? Probability of choosing the first number from set S1 times, now you need to choose the second number also from S1. So this is like probability of choosing first number from S1 times probability of choosing the second number also from S1 given that the first number was from S1. Right? Or probability of first number being chosen from S2 times probability of second number is also from S2 given that first number is from S2. Right? And since first and second numbers are independent of each other, this will be very easy to calculate. The probability of second number being from S1 given that first number is also from S1 is nothing but probability of second number is from S1. Right? Since these two events are independent, it is given to be independent. Right? So this will not have any impact. So what is the probability of first number being from S1? It is 7 by 13 times the second number is also from S1, given that the first number is from. So first number and second number are independent. It doesn't matter. So probability of second number being from the set S1 is again 7 by 13 plus probability of first number being from set S2, it is 6 by 13. Now probability of second number also being from S2, given that first number is from S2, so they are again independent, so it is also 6 by 13. So you just calculate this. So it's 49 plus 36 over 169. You can calculate using calculator. Okay, you'll get 0.503. So there are around 50% chances that both the numbers will have same most significant bit. Cool. So these were a few questions from total probability. In the next lecture, we will see the most important theorem of all. It will combine everything that we have seen so far. It is the Bayes theorem, and that will conclude the basics of probability. Cool. Thanks. Bye bye.